in the previous session, we were discussing about the CAN protocol, and let's go through quickly about what we had discussed earlier. All right. So it's CAN with the full form controller area network, mainly developed for the automotive applications by Robert Bosch. All right. So almost 30 years ago. So again, there was a requirement that whenever we have multiple ECUs present in the system with the various types of input and output, right? So you need to have a common, what you call, common bus system and common protocol to connect multiple ECUs present on a vehicle, okay, in the automotive domain, right? So this was developed, and we can see something like this, right? There are terminating resistances RP, right, fixed value like 120 ohms, and we have simple two wires. One is CAN H and CAN L. We connect the various nodes like this: one connection to the H line, one connect to the L line. Like this we can connect any number of the uh, the ECUs. Here we call it as a node, right? Every device that you connect to the CAN system is a node for us. Okay, we then we checked what is the requirement. Why did the why the Robert Bosch actually invented that, right? So reason is, before the CAN, the connection would have been something like this, right? ECU1 to ECU2, maybe, right? One of the device will take three lines as input, some other device will take one line as input, output, right, etc. The basic problem we are going to face is, how do you add a new node to this, right? Whenever I'm adding a new node to this, right, the new node, maybe ECU6, whichever you connect, should have its own protocol to connect with all the other five nodes. So you need to develop five different protocols, basically, right? That is a very difficult job. So to overcome that, right, they developed a two-wire system. Anything you can add, right, or remove from the system, right, without affecting the current performance or current orientation of the CAN network. So that's a major advantage. Other than that, we also have seen few more points over here. Okay, right. So let's move further. uh, the physical or the layers of this particular protocol is something like, you can use only two layers. If you remember the OSI layer or any other networking layer, we used to have at least five or seven layers, right? Again, that is an advantage here, right? We just use the data link layer and a physical layer. Only two layers are sufficient. Other layers are basically not at all needed. So that is another advantage, right? Another fundamental advantage of this kind of the CAN protocol, basically. Okay, all right. So then we just introduced the various types of messages present in the CAN system, right? One is data frame, second one is called as a remote frame, and the error frame and the overload frame, right? We just defined them in the previous class. Right now, our intention is to look at these data frames, right? Look at the various types of messages in detail. So we are going to look at the data frames first. It's a first type of the frame, data frames. All right. So basically, this data frame is responsible for uh, transmission of the data, right, by a node. Whenever a node wants to communicate, data frames will be used to carry the data. Okay, as the name suggests. So I'll just write one point here: used by the nodes, right, to transmit the uh, data to other nodes by using the CAN. All right. So normally we have two types of data frames possible. One is called as the normal data frame. When we say normal, it's the simplest possible format. But when you have a larger data present, when you want to send a bigger data, the normal data frame can be converted into an extended frame, right? We have two options. right? You can either send the simplest format or the extended format. All right. So what are the various fields present inside this? We'll see now. Okay. So there are various fields present. So I'll make a table just to easy to remember. So this is the field. Then each field may have a subfield present. Okay. So I'll write the name of the subfield in a different column. Then we'll write the length. All right. So what will be the length of each of them? Okay. So this is what we need to remember whenever a question comes on. We need to discuss about the data frames, right? So first one is called as the it's called as a start. Field is called as a start. We don't have any sub field in that, so I'll write the name itself. It is a start of the frame, right? It's not a subframe, it is a frame itself, right? So the length of this is now I'll write maybe length in bits, okay, so that we don't have to remember how what is the way of representing them. All fields will be mentioned here in the form of bits only, so it's of size 1 bit. All right. Then the next field is called as the arbitration. So inside the arbitration, normally we have two subfields possible. The first one is an identifier. It's a ID, and we have another field called as the RTR field. We'll discuss about this later, right? Just remember that names. That's all. So for totally arbitration is 12-bit field, out of which 11 bits are the identifier and 1 bit for the RTR. All right. Then let's move further. Then the next field, okay, I'll try to make the groups so that it becomes easy for us to understand. Okay, so this is the heading, and this is one field is complete. Then I have another field which actually includes two subfields. All right, arbitration includes these two. Let's move further. Then the next field is called as the control. Right, in the control, normally we have three subfields, right? One is called as the IDE field. Then we have a field called R0 and another field called DLC. Okay, so this basically DLC is the data length carry field. So anyway, I'll come to that later. Here, let me write the sizes. All right, so totally 6 bits is the size, out of which the IDE takes one bit, the R0 is 1 bit, and the DLC is actually 4 bits. All right, so when the 4 bits are used, you can represent a number from 00000 to 1. So that's the okay. All right. So the next field is the actual the data. Whatever data we want to send, we will send that. So the fields could be represented by the registers D0 to D8. So this means there are 8 registers. Each register is of size 8 bits. So how much is the size? 64 bits. All right. So that's the next field that we are going to send. Then the redundancy check, right, has to be performed by the data field itself, right, size, for which we are going to use a CRC field, right? Cyclic redundancy check, right? Have you heard the term somewhere? CRC, right? Okay. So it's just a redundancy check. So there is a CRC field and a delimiter field corresponding to this. So normally we have 15 plus 1 bit, so totally 16 bits. That's the size of this. Then whenever somebody is going to acknowledge, or the one who is sending this message needs to acknowledge to something, right, which has been asked by any other device, you need a field for acknowledgement. This is acknowledgement field. So this is ACK, the field, one of first sub field, and there is another delimiter. So acknowledgement is 1 bit, delimiter is also 1 bit, right? So after that, we have a very special end of a frame for CAN bus. So that is end of the data frame, Okay, so that is denoted by EOF, right? It's actually 7 bits, right? The very specific idea is that you need to send 7 ones continuously to say that, yes, I am finishing my data. Okay, right. Anyway, I'm going to look at that now. Right. So as of now, we understood that these are the various fields present in the whatever in the data frame of the CAN. Right now, we'll see an example. Okay. So let's try to. I'll directly give an example so that we understand that how the what is the format of a exact data frame, right? So let's write an example. All right. So as we see, right, we need many bits to be represented over here. So for that reason, maybe I'll try to write in a very small space. Okay, let me try to start from here. Let me assume that this is the data frame. All right. All right. In this, let me draw the first bit. So I'll say it is 0, right? First bit I'll make 0. If you remember, this is the start of the bit. Okay, start, right? So first bit becomes 0, let me assume. Okay, so this bit itself is the start of the frame, right? So I'll write the values over there, and what exactly I'm writing, I'll write here. So this is the SOF frame, right? Start of the frame. Right, then you see we have to use how many, next one is an identifier. Okay, so this identifier is nothing but, right, I have to tell uh, which is the address. Okay, that's the identifier you can see here, right? 11 bits of identifier and an RTR, right? Right. So I'm going to use the same idea here. Let me write what I'm trying to send here. Something like maybe. Okay. So I'll tell you what I'm trying to send. Okay. So example, I'm actually a ECU. Let's assume, right? The ECU sends, say, 1 byte, right? This is the data. What is the data? Let me say it is 0x02. This is the data. 1 byte, 0x02 uh, on the canvas, right? To, say I give a device, right? To an identifier. Say the identifier has an address like 0x, maybe 02F. Okay, so this is the identifier. So you see, right, our the device which is trying to communicate should put the identifier next. So I'll put the identifier, right? What is the identifier? According to this particular example, it is 0x02F, isn't it? Okay, so let's write the 11-bit representation, because if you see, there are total 12 bits to be assigned, right? So out of the 12 bits, 11 bits will be used for the identifier, next 1 bit for the RTR. Okay, right. So what we do now, so always if it is a what you call, if the data that you are sending, if it is a data frame or maybe a remote frame, right, then there will be, right, we are going to put that as 1. Okay, so if you are trying to receive something, right, it will be 0. If you are sending something, the RTR frame becomes equal to 1. So that's the rule, right? So because of which, now I'm going to write the 11-bit representation first. So what's the 11-bit representation of the identifier? So just see, it is 2F, correct? So 2F means I just need 6 bits, right? 1 0 1 1 1 1. So remaining 5 bits will be 0. So 1 2 3 4 5. Remaining how many bits? 6 bits. I should fill the 2F. So 2 is this one, 1 0, right? Then F will be 1 1 1 1. Is it okay? Right. So this is the identifier. So followed by the identifier, I'll put the RTR. So it's right. Are you receiving or transmitting? Right. So it's that way. RTR stands for that. So now you are not receiving, you are sending. Okay. So if you are receiving, it will be 1. You are sending means it is going to be 0. Okay. Just remember. So now what I should put here, it should be a 0. Okay. 0 for it. Then, right, I have to use what is called as the next bit, which is IDE. It is a control bit. Okay, so IDE is going to remain 0, right, for the frames such as the what is the other frame name? I forgot. Okay, so remote frame as well as for the what you call the data frame, the next ID remains equal to 0, right? So next frame is the I, D, E. So since this is a data frame, I am going to keep that as 0, all right? Right, so this becomes 0, followed by a register value, that is R naught, right? It will also remain 0 for this particular whatever data frame we are sending. Okay, so make that a 0, followed by, if you see, I have to go for, after this, just check. I need to write a 4-bit DLC control part. Okay, so again, you are trying to send means it is 0001. There are various options available, but for the time being, we are sending a data. So the control bit for sending data is 0001. So 4 bits 00001 will be the required control bit for this operation, right? So that will be the DLC. Then you see the data comes into picture. So what is the data now? The data is 0x02, isn't it? So I know that there are 8 bits allocated. So 02 means 00000010. That's all, right? So that will be your data which you want to send from the current the ECU to the next one. All right. So again, as of now, we have no idea about what CRC is going to do. What will be the actual value of CRC possible? But we'll write a some representation for CRC. Okay. So next, we need to show that there will be a CRC, right? So the most common number which is used as CRC. Do you have any idea? Are you able to recall the CRC concept? And if you remember, you tell me. Otherwise, I just write the answer. Okay, right, no issue. All right, so in the CRC concept, one of the commonly used data is 2411. Okay, so that's a number we are going to use, right? So look at the space available for CRC first, right? Then we'll see. So I have 15 bits space available, right? So in the 15 bits, right, I have to send this number, that is maybe 2411. So the equivalent representation I'll write, you just check. Okay, so 0 1 0 0, then I have 1 followed by 1 2 3 4 and 5 zeros, then 1001. So just count 1 2 3 4 5 6 7 8 9 10 11 12 13 14. I missed a 0, I guess. So this is 0. Oh, yeah, I missed a 0. So this is 0, followed by there is a 1. Now the count is this. So you see 1, 1. So I get a 1 here. I get another 1 here, followed by a 4 here, then a 2 here, right? It's correct. Again, it's as of now, no particular reason for writing this as a CRC, right? You can use any other CRC values as well. Okay, there are many CRC values exist, right? But when we actually develop something, we'll use the proper one. We have to design that value, okay, not a random one. Okay, all right. So followed by this, you see the 16th bit of our the CRC is nothing but there is a D, it's a delimiter. I'll just write delimiter. delimiter will be always used as 1. Okay, then you need to acknowledge that you are sending something. So the acknowledgement, I'll slightly move to the right. Okay, so the acknowledgement should be coming after this. So ACK, if you remember, acknowledgement is 1 bit. So that will be a single 1 over there, right? Acknowledgement should be followed by another delimiter. Okay, so delimiter is always 1, right? Now you see final one is the end of the frame. EOF is very standard and very unique when it comes to uh, the scan protocol. It's 7 ones. All right, 1, 2, 3, 4, 5, 6, 7. So when we send a frame like this makes a valid frame for sending the data in case of the uh, CAN protocol. All right. So we just sort of remember that table, and we can give any sort of examples if you want to give example for this data frame. All right, so that's how a data frame looks like. I think most of the time one question will be something like just explain, right, is the most common question, right? So just tell that, okay, these are the various frames, the various fields, and this is an example. All right. Now, what is the difference? There is another. Whenever your data is large, right? You will this length is not sufficient. Okay. So there is a possibility of sending the extended data frame. Right. Very simple. Not a huge difference between this. Right. The arbitration field will not be there. That's the difference. We'll write only the difference. Okay. So no arbitration field in case of this, and the data frame identifier, right, is changed to 29 bits instead of the original 11 bit. Okay, so the data frame identifier is changed to 29 bits. That's all. So originally it was 11 bits. Now you see it is extended. That's all. Right. So that's how we get the extended frame. All right. Fine. The second frame that we use in the CAN protocol is called as a remote frame. Okay, so when the remote frame is used, if you remember, we just wrote one sentence. What is the application of each of the frame? So any node can broadcast its information anytime. All right. So in the sense, because whenever a new device gets connected to the canvas, right, all the other devices connected to the canvas should know that yes, somebody new has arrived and they got connected to our system, right? Something new comes means nobody knows its address, right? Correct? No identity. Sorry, the identifier corresponding to that particular device is unknown, right? So you need to keep sending periodically whenever the bus is free, nobody is transmitting means you need to keep sending your information. This is called as a broadcasting. Okay, so every node is required to broadcast its information, right? Either periodically or at any point of time, whenever it is getting connected or whenever it is, whenever you are trying to remove the device from that, you will send that, okay, I am no more existing in this network, right? And so on. So, okay. So periodically we send the information of each and every device or the unit that is connected to the system, to the CAN system. All right, that's one thing. Also, sometimes any ECU can request another ECU present on the CAN bus, right, to send an information about that device. Okay, so this request of the information is what is called as a remote frame, right? So two things you need to talk about a remote frame, right? Say a node connected to the CAN system uh, should, it has to broadcast. Okay, it has to broadcast its information periodically or maybe anytime. Anytime it has to. Somebody requests means you can, right, definitely send that. Okay, anytime, right? So this can be done. Or there is another point, right? The information, maybe some other device may request, right? So one ECU can request other ECU on the CAN system, right, to share its information. It is possible, right? Two things are possible, right? This particular request, right, is done through the remote frame, right? So the remote frame is used to handle the requests. So such a request we try to handle through what is called as a remote frame. So normally you see that we don't have, it's just a request, right? There will be no data present in it. Okay. So that's one thing. So just remember about the data frame. Whenever we explain, we need to talk about one thing. So no data field in the remote frame. You're asking for it. Whatever information you want. You are requesting the information. So no information will be present over there. Okay. And the next important thing is the RTR field, whatever we had, it will be equal to 1. Right, all other fields we are already familiar with. Let's quickly go through the table, right? So what are the various fields present? So the various fields, if at all I can write a subfield, right? Then we'll write the length will be in bits, right? So we know that we have a start frame, that is SOF, short form. Length is 1 bit. Already we know that. Then we have another field called the arbitration. We have an identifier field followed by the RTR field. So we already know that there will be an identifier of length 11 bits followed by the RTR, which is 1 bit, and we also know its value should be equal to 1 as per the rules. Okay, so that is the second field with the two subfields. Okay, so this is a 1 followed by, let's say, this one. Okay, so below after that we have the control part. We know that the control part has three things. One is the IDE, just now we have seen that. Then we have R0, one single bit, and a DLC. All right, so these fields are of the same size like previous one bit and 4 bits. Okay, then let's go to the next part. Over here, right after the control, you know that we need to use the cyclic redundancy check, CRC, right? So you have a field by the same name, that is a cyclic redundancy checker of size 15 bits, right? And we have a delimiter. Okay, so the delimiter is of size 1 bit. Right. So followed by this, only the data frame which we had earlier, right? That is absent in this because you're simply making a request. So next one is a acknowledgement, right? So acknowledgement will have a field by the same name, ACK, right? Size 1 then the delimiter, right? Delimiter is also 1 bit, right? Last, we have the end of frame, right? Again, the end of frame is unique in case of the CAN protocol, right? So that is EOF. So has the same field by the name EOF, and 7 ones are required to stop. Is it okay? Right. So no data frame at all, right? Don't send the data. Other than that, you need to send, right, the other values. So I'll directly copy the previous one. Otherwise, it will take time writing that. So I'll make the modifications over there. Okay, whatever data frame I have written, I'll simply copy that. Okay, so this is how we can expect the frame to be. And remember one thing, we will not be using the data frame, right? So the data should not be present over here. So what I do, I'll just erase this part and I'll club the remaining parts together. Okay, so I'm not going to have the data. This is not there. Okay, and let's copy this and let me bring this to touch this. So whatever you see here itself is the required. Is it okay? Right. So you see, I'll write what I'm trying to write here. So this particular in this particular frame, one of the ECU is making a request. Okay, it is making a request saying that what is the okay. I'll write just below this so that it's easy for us to trace it. Okay, so right. So here in this example, right, this example ECU is requesting another ECU, but it's not a general, right? Another ECU with an identifier, okay? With ID of the one whom this ECU is requesting is this one, 0x, sorry, what's the identifier? 0x02F, right? There is one ECU connected to the CAN protocol whose address is 02F. That's here, right? You are requesting this particular ECU, right, to send information, right? Again, you are saying that what is the length of your frame, right? Okay, send the information of size equal to size equal to 1 byte. So how do you identify that it is 1 byte? I'll tell you. So you see this one, whatever you have written here, right? This is the size part. Size equal to 1 byte, I decide by this. Okay. And again, so you are requesting something to send. The request part comes because this is 0. Okay. So it is as of now. Okay, sorry, I made a mistake. So previously it was 0. I think I copied 0 directly, right? So that's why it is 0. It is 1 for the remote frame mistake, right? So how do you identify whether it is a data frame or it is the request frame, right? I will make change. This is 1, right? So if you are using this as 1, it says that it is the remote. Remote frame, it is 1. So you can go back and check the previous case, we have it as 0. And the difference between this frame, the remote frame, and the previous frame is that, right, there is no what you call as the data. Data is not present. That's all. Okay. So it's a standard form of sending a remote frame in case of what is called CAN protocol. All right. Hope it is clear. Let's move further. The next frame, if you remember, it is called as an error frame. Okay. Now, if at all this is very simple, you don't have to write a actually write a fields etc required for that, because the if at all there is an error, it can be identified very easily by anyone, any device that is present on the CAN system, and it can send only 5 consecutive bits of the same polarity. That's all. Either send 5 zeros or either send 5 ones. That is enough to identify that as a error frame. Okay, error is there. There is some error occurring in the CAN system, or the CAN protocol is not being validated, or it's not properly being executed, means there is an error. So any device which identifies that error, right, you can simply perform the following steps. All right, so I'll just write what we are supposed to do that. So according to the CAN standard, we need 5 so consecutive 5 consecutive bits of same polarity. All right, same polarity between, there is a condition. It's not like randomly you send 5 bits. All right, between the SOF, what is that, start of the frame, okay, and the CRC, between them you should send. That's the only condition. Okay, between the SOF and the CRC field of the message, field of the message. Okay, right. Now, if any ECU wants to send more than 5 consecutive, then there is a slightly different concept. We have to use what is called as a bit stuff. Okay. Otherwise, what happens is that every node will detect that, okay, there is an error. What if your message itself has more than 5 bits? Correct. There is a question. Correct. Are you okay? So let's assume that there is one device which wants to send the data, and data is more than 5 ones. Correct. Possible. Correct. So if that is the case, then you have a you need to do perform what is called as a bit stuffing. We'll discuss the bit stuffing as well later. But as of now, just remember one point, that if a okay, I'll write ECU. If a ECU wants to send more than 5 bits of ones, then, right, what has to be done, right, it has to follow a concept called as bit stuffing, right? Why you need to do that? Otherwise what happens? The receiving nodes think that there is an error, right? As soon as 5 ones come, means okay, they will think that, okay, yes, this is an error, right? Otherwise the receiving nodes detect error. That should not be happening. Right. So normally, according to the CAN standards, the error frame will have 2 different fields. All right. So in the CAN protocol, any error frame, has 2 different fields. Right. So what is called as a flag will be used, right, as a uh, maybe 6 to 12 bits in general. Okay, so the first one is called as the error flag. right? As we may think that flag means it is a single bit, right? But no, it is not a single bit. It can vary 6 to 12 bits in in terms of the length. Okay. Then the second field is the error delimiter, right? This will be up to, no, it's not up to, it's a fixed 8 bits, right? So that's how so more details about this we can study when we go for the bit stuffing. All right, so as of now we are simply discussing about the structure, that's all. No details required, right? What are the different frames in that, and what are their structures, right? We are trying to answer that part. Okay, so that's the error frame, right? Then we'll move on to the next frame in the can. It is called as the overload. All right. So, as we have seen when I just brought the word in the previous section, previous session, that there is a frame called as overload, and it is very similar to the error frame in the format. And I think I have mentioned that it gets it transmitted by any node to buy some more time, extra time. Right now, it has been allocated so much time to do a read or write operation, but that time is not sufficient, right, for that device. So it can make a request saying that I need more time. You buy some more time if it is too busy so that it could not complete the work and now it needs extra time to complete the work. All right, so that's a overload. As the name suggests, you are overloaded, right? Within the time you couldn't finish, you need extra time, right? So it's very similar to the error. All right, and it is it is transmitted by any other, or okay, any node, sorry, not other. It is sent by uh, any node to this to buy more time. Okay, as it could not finish the job within the allocated, or it may be a stipulated. So whenever it is given, it will be decided that okay, every device gets 10 milliseconds of time to finish something. That's a stipulated time, right? So within the time. So you ask for more time to finish the pending job. Okay. Uh, Normally you see that the actually we have the current can systems are not using the overloaded frame as it is, just because of the reason that there is a separate controller available to do this job, right? There is a separate hardware available, but right now what we're discussing is the simplest format of the can, right, where there is no control. Okay, can you might have heard about the vehicles which are coming nowadays. You say that can controller is present. Okay, so some they will say that okay, this vehicle is installed with the can controller. So you see there is a controlling device. There is a separate hardware available to do this job. Who gets what, how much time, and some of the devices are not able to finish the job within the time, so the controller will take control of the whole thing and they will allocate extra time needed or whatever some so the preference is given to what you call a device, like okay, if there is a request from this particular device, give the preference, all the other device should wait, right? What do you call that as the interrupt concept? Have you studied the interrupt priority precedence rule, correct? So everything will be now as you see here, there is no concept of such things, right? That's not what we are studying here, but the current can latest can which is in the market since last 5 years or so, right? They have a CAN controller. Controlling is separate device is fitted with the CAN bus so that it can control every device connected to that. Okay, so because of that, overloaded frame may not be present in the current system. All right, but anyway, I'm not going to write that over here. That's just an additional information. Right now, so we understood that there is a similarity between the error frame and the overloaded frames. Okay, so now I'll tell you why there is a requirement of the what you call as a controller. Why they brought the whole new concept of adding a separate hardware to the canvas so that it can do a controlling of everything. So it was there were some difficulties in identifying the error frame and the overloaded frame by not all the devices connected to the CAN system, but by some of the devices. Okay, because as I told, it looks very familiar. As you can see, the first sentence written here, similar to the error frame. So that means error frame and the overloaded frame are very similar to each other. So some of the devices are are not able to differentiate between them. Correct. So you see, this is because overload frame normally starts after the whatever space is allocated between the two messages, right? So it looks like, right, something like maybe so maybe we have, I'll just write a diagram. So let's say this is the time, right? The horizontal axis is the time, right? One frame is over, this is a frame one, let's assume, right? Normally you give a small gap between them, right, so that the second frame can be sent after. This is frame two. Any frame can be present here, it can be data frame, remote frame, or whatever. Okay, like this. So normally what happens is that the overload frame, where it should start according to this explanation whatever I have given here, right? What do you think, where the frame, that frame is going to start? So this will be my frame 3, give a space, frame 4, and so on. I have this available with me. Okay, so this, after this I have frame 5 and so on. So my question is that, what do you think, where the overload frame is expected to start? Hmm. If at all I am sending, see, let me assume that I am a ECU and I had been allocated this time F1, complete this frame is my frame. But within that frame time, I am not able to finish the job. So I have to send a overloaded frame, correct? Immediately after that, requesting that I need more time. So where do you think I should send that message? Yes. So anyway, so we know that I have to initiate somewhere here, right? Maybe here this is where you start. So that's my point, right? Overload frame always starts after the allocated time for this current frame, and maybe right before the next frame starts. Correct? But you see, what should be the error frame, right? Where the error frame is going to start? If at all there is an error, right? I send a F1. While sending F1, some other device detected an error. Correct? You see, error may get detected at any point, right? So maybe here this is the point where some other device detected an error. Okay, error detected. But right, anyway, this time duration is allocated for the current whoever is sending, right now one ECU is sending, it is allocated to that. So immediately after it stops, somebody will be ready to send the error message, error signal. So you see, this was the problem is that your request as well as the error being sent at the same time. So nobody, some of the devices find it very difficult to understand whether the signal being sent is an overload frame or an error frame. Two things are there. One is that they look very similar. Okay. They look very similar. Again, the second point is that most of the time, the overloaded frame as well as the error frame, they will be sent at the same time. Okay, in the most simple format of the CAN, this was the issue. Okay, so later on you had to eliminate this because you are connecting, maybe nowadays 2025 different ECUs are connected in a car to the CAN bus. So the complexity is too huge. You cannot keep debugging the whether the frame is error frame or overload frame, right? You cannot keep tracking of that, right? So for that reason they brought the whole new variety of the CAN bus, wherein you have a CAN controller, right? That will decide, right? That will alert every device saying that yes, this is an error frame, and it will say that no, it is not an error frame, it is a overload frame, right? So slightly modified CAN is what we have right now, right? Anyway, but since our intention is just to understand the concepts of the CAN in the most fundamental fashion, right? We'll not say that okay, there is no overload frame in the CAN. We'll say that yes, overload frame do exist and this is how it looks like. Okay, but if you want to extend that answer further, you can say that in if while using the overload frame, this is what is the problem. Okay, right? Error frame starts at the same time when a device sends the overloaded frame. So some devices may feel difficulty in identifying whether the frame is overloaded frame or an error frame. Is that okay? Yes. So those are the four different data frames present in the CAN system.